Hello everyone, how's it going? Hope you all are doing well. Welcome you all to this channel. Here is a brief profile about me. So today my friends will start the remaining topic on chapter number 2. So till now we have covered what is pressure, how the pressure is defined, what is Pascal's law and its validity. Also we have learned about hydrostatic fluid. And today my friends will cover pressure measurement techniques and various devices, for example piezometer and manometer, and we'll learn how these devices functions. So let us start our first topic, that is pressure measurement unit. So basically till now my friends we have learned various unit of pressure, that is one is Newton per meter square, other is Pascal, and one is bar. So these are the three units that we have learned earlier lectures. Okay, and today we'll learn these three terminologies, that number one is absolute pressure, second is gauge pressure, and third is negative gauge pressure or vacuum pressure. So let us try to understand what this terminology means. So absolute means, as this is absolute, so this is from the bottom, right? So from the basic, that is from zero, whatever is the pressure that is measured is called as absolute pressure. For example, let us try to understand by graph. So I say x as a datum line, okay, and on y-axis I have a pressure. So here it will be 0, right? So this is the datum line. So if the pressure is measured from the datum line, then it will be called as a, so let's suppose this is the pressure point, and if it is measured from datum line, then we call it as a absolute pressure, right? Be it any point from here, if we measure from the bottom, right, from here, these points from here, right, so this we call as a absolute pressure. And let us consider a constant pressure line that we call as a atmospheric pressure line, that is PATM. What is the value of PATM? Atmospheric pressure is 1 atm, or we can say 1.013 bar. Okay, so if this same pressure is measured from here, from this point, right, from this point, if I measure the pressure, then we call it as a gauge pressure, and it is in upward direction, that is in positive direction, so we call it as a positive gauge pressure. But if I measure this pressure point from here, not from the absolute datum line, but from this line, that is atmospheric pressure line, right, so in that case it will be called as a negative gauge pressure or vacuum pressure. So these are the three terms. One is absolute pressure. When the pressure is measured from the datum line, then we call it the absolute pressure. When it is measured above the PATM, for example, what is PATM is 1.013 bar. Now I say here absolute pressure is 10 bar. Then what is the gauge pressure? 10 minus this value, right? So 10 minus 1 bar, that is 9 bar, is the gauge pressure. When the absolute pressure is 10 bar, then the gauge pressure is 9 bar, approximately 1.013 bar. If I will subset, this will be approximately 9 bar. Okay, and if I say absolute pressure is 0.8 bar, so what does it mean? It means that I am measuring from the datum, that is from x-axis, from 0 it is 0.8 bar, means the line length is 0.8 bar. What is the length of this line here? It is approximately 1 bar. So what is the vacuum pressure here? Is 1 minus 0.8, that is length of this line is 0.2 bar, or I'll say minus 0.2 bar gauge, 0.2 bar vacuum, right? So this is the representation. If I say gauge pressure is 2 bar, what is the absolute pressure? This is the gauge pressure. Then absolute pressure is nothing but I'll add the PATM onto this, then it will become 2 plus 1, that is 3 bar. So now my friends, I hope it is clear to you all these three statements, what is absolute, what is gauge, and what is vacuum pressure. There is one more statement that is very important. Vacuum pressure doesn't mean that pressure is zero. It means that pressure, by how much amount it is below the atmospheric pressure, that is called as a vacuum pressure, right? So I hope you understood, right? By how much amount it is below, this is the atmospheric pressure line, let's suppose. So by how much amount it is below this atmospheric pressure is called as a vacuum pressure, right? So this is the length of this line. So now let us move to next topic, that is classification of measuring instruments. So what are the various measuring instruments? How these instruments are classified based upon their principle, we will learn in this slide. So the very first classification is on the basis of column. What is column? Previously we have learned what is column, right? So basically column is nothing but, if I have a pipe, right, in this I have filled up a fluid, this is called a column, right? So here that it is free surface, so here the pressure will be atmospheric. And if I ask you to find out the pressure at height h below this point, then how will you find? PATM plus rho GH, where rho is the density of the fluid and G is the gravity, right? So this is, we have learned previously, that is column, right? And in column we have learned two concepts that we'll discuss later once we'll see this pressure measuring instrument classification, right? So on the basis of column, it is classified into two, that is simple manometer and differential manometer. In simple manometer, it is classified in various groups, that is called piezometer, and then U-tube manometer. One by one, my friends, we will discuss these devices, okay? And then single column manometer. In differential manometer, it is classified into two groups. One is U-tube manometer, that is differential U-tube manometer, okay? And second is inverted. This U-tube manometer and this are different. This is simple manometer type of U-tube manometer, and this is differential U-tube manometer. And the second type of differential manometer is inverted U-tube manometer. And based upon principle, the other group we call as on the basis of elastic properties. on the elastic properties that we call as a mechanical gauge. So it measures gauge pressure, right? Mechanical gauge. So one type is called as a Bourdon tube. So let us start with piezometer. So piezometer is nothing but it is a simple manometer. Its both ends are open with one end where the pressure is measured and other end in the atmosphere, right? So it is nothing but a simple manometer. For example, this is a pipe, okay, and I want to measure the pressure inside this pipe. So I fitted a piezometer here, right? This is one end of the pipe and this is another end. The one end is open inside where the pressure is measured and the other end is open to atmosphere. So when this is open, the fluid will come here, okay, and it will rise in this column, right? So if I want to find the pressure here, so this is the free surface. So here what will be the pressure? P AT, right? And I want to find the pressure here. So now, as per the Pascal's law will be valid here, right? Because we are talking about the fluid statics. We in pressure measurement devices we assume that fluid is in static condition. So as we learned in Pascal's law that in horizontal direction, that is perpendicular to the acceleration due to gravity, the pressure remains constant because there will be no pressure gradient. The pressure gradient will be only in the direction of G, right? That we have learned, that is pressure gradient, that is delta PdP is rho G into delta H, right? Pressure gradient is nothing but delta P upon delta H is minus equals to minus rho G, that we have learned in previous lectures. So as we go down, the pressure will increase. This is the negative sign. When we go up, the pressure will decrease, right? So this is what we have learned in previous lectures in column. So this is the column, right? And I have 2 points here. This is let's revise this concept, okay? So if I have given the pressure here, I want to find the pressure at this point P2, right? So what is the P2? P2 is nothing but this is column, right? So I am going vertically down. So P2 is nothing but P1. As I am vertically going down, then plus rho G into H, right? And if I want to find P1 given the P2, right? I want to find P1 given I am having P2, right? So what I'll do, P2 and I am moving up, so I'll do minus rho G H, right? So this is the only two things that you have to remember. And similarly we can derive this differential, right? So what is P2 minus P1 is nothing but rho G H, right? So H is in downward direction, right? So this is the differential pressure delta P, and H in the downward direction is negative, right? If I'll consider upward, this Z as a positive, upward as a positive. So in this condition I have taken this point. So in this condition P2 minus P1 is delta P and H will be nothing but minus delta H. Okay my friends, so this is the revision of the concept about the pressure gradient. and these are the two things that you try to memorize. And in every questions of the manometer or be it any, you don't have to see whether it is in problems, you really don't have to see whether it is piezometer or manometer. You just try to use this concept and the problem will be solved very easily. Only these two concepts. Okay, so now let us try to learn piezometer. So here what happens, the Pascal's law says that pressure P remains here, so here the pressure P come, right? Okay, so now this height, let's suppose this height is H. So now I am having P here and I am moving up and I am reaching to this point, and here the pressure is P atm, right? So if I'll do P moving up, so minus, what is the density of the fluid, rho G, I have moved up H height. Okay, so P minus rho G will be the pressure at height H, and it is free surface, so this pressure will be nothing but P atm, right? So what is P now? P atm plus rho GH. So if I measure this height H, then by putting the density value and atmospheric pressure, I can evaluate the pressure P, right? So this is the basic concept of piezometer. But there are disadvantages with this device. What are the disadvantages? You please think by yourself, right? So let us consider this is air itself. This is nothing but air. So you will be not able to differentiate between this point and this point. It will be the same altogether, right? So you will be not able to find the pressure in case of gases, air, nitrogen, oxygen, because if you make it open, these gases will diffuse in atmosphere and it will be not having any differential point, right? The second disadvantage is it cannot measure the vacuum pressure. This is the first disadvantage. Second is it cannot measure the vacuum pressure because it takes the reference of atmospheric pressure itself. Okay, so any pressure which is greater than atmospheric pressure can only be measured. Any pressure which in absolute term is greater than the atmospheric pressure, then only it can measure the pressure. Otherwise, if it is below this atmospheric line that we have studied previously, if it is below, then it will not be able to measure, because this is below, then it is called as a vacuum pressure. And as it considers atmospheric pressure as a datum line, as a basic line, hence it won't be able to measure the vacuum pressure. The third disadvantage is for high pressure and low density fluid, right? So if I say this pressure is very high and density is low, so the H value will be very high. You can evaluate this. If what pressure is high and density of fluid is low, then this leads to very high amount of deflection in this pipe, and then you will be needing a very large length pipe, which will be not possible for a particular device because of space constraints. So because of that, it is not suitable to use piezometer in case of high pressure with low density of fluid. Okay, so to overcome these disadvantages, what scientists and engineers, they have come up with another idea that is called as a U2 manometer. So basically this is the development phase in earlier days. At first they have used piezometer, then they thought no, piezometer is not sufficient for our application. So to overcome those issues, the scientists and engineers have come up with another idea that is called U2 manometer. So let us try to understand what is U2 manometer and how it functions. So I am having a pipe. In this a fluid is flowing, right? Here the pressure is P. And now I have connected U2 manometer. From name itself, it will be having a U tube, not a straight tube that we had in piezometer. Okay, my friends. So this is the U tube. Okay, And in this will be the fluid, that is where you want to measure the pressure. And now we will be having a manometric fluid here, separate fluid. Okay, my friends. And this fluid can be anything, okay, but for our application we will learn that for a particular specific area you need different kind of manometric fluid. This fluid we call as a manometric fluid. So based upon the application, this fluid can be anything, okay, that we'll learn. So now let us try to understand how to measure this pressure. So it is very simple. Now let us consider this density is rho m and here the fluid density is rho f, okay, where I want to measure the pressure. So here the pressure is P. So in horizontal direction, as per Pascal's law, the pressure will remain same. So here it will be the P, right? And now I am going down. Let's suppose this distance is h1, okay. So if I have gone down by h1, so what will be the pressure here first? Here the pressure will be P plus, because I am going down, what is the density through which I am going, right? This fluid that through which I am going, right? So rho fluid into G, how much distance? h1. So this is the pressure here. And as per Pascal's law, if this is the same fluid, right, that is manometric fluid, in horizontal direction the pressure remains same. So here it will be the same. This will be the pressure, that is P plus rho f G h1. And now from here I am going up. Let's suppose the height is given h2, okay. So here I know the pressure. What is the pressure? P plus rho f G h1. Now what I am doing? I am doing from here to here, right? I am going from here to here, that is upward. So minus, what is the density? Rho m, because I am going through this fluid, manometric fluid, into G into, what is this length? h2. So now I have reached to this point. So this is the pressure here, right? And what is this? Is the free surface. So here the pressure will be P atm. P atm. So now I can evaluate P, right? It is nothing but P atm plus rho mercury GH2, rho manometric fluid, minus rho f GH1. So now you have to use only this concept in solving any problem related to the manometer or piezometer. If you follow these instructions properly, these concepts properly, then you will be able to understand it in a much better way, and the questions you will solve in 1 second. In one line you will solve the questions, okay. So this is about the U2 manometer. So what is the advantages of the U2 manometer? Because here we are having choice of fluid, manometric fluid, then we can use high density fluid. In that case, if I am having high density, right, high density fluid, then I can measure very high pressure, right? If density of manometric fluid is very high, then in that case I can measure very high pressure. Are you able to connect these things? In piezometer we didn't have any separate manometric fluid, right? But here now, as we have a different manometric fluid, so there is a choice. So if I want to measure a high pressure, then I'll use very high density manometric fluid. And also if the fluid is very reactive, then I'll use a manometric fluid which is not reactive with the fluid which I am measuring, because they are coming in contact. Secondly, piezometer was not able to measure the gaseous pressure. Now, because of there is manometric fluid which is of your choice, let's suppose you are using a mercury, then you can have a gas here and gas here, right? So you can measure the gas pressure as well. So basically this U2 manometer is taking into consideration the points that piezometer could not resolve. This manometer, U2 manometer, is solving those problems, those issues. Okay, as the last but not the least, manometric fluid is different and can be preferred according to applications. So my friends, now we'll learn about single column manometer. So this is nothing but a modified form of U2 manometer in which one side is a large reservoir and the other side is a small tube. So let us try to understand this. So in this case, as statement says, we'll be having a large reservoir on one side. This is a large reservoir and it will be connected to a small diameter pipe. Okay, and it will be filled with a manometric fluid. Okay, so now it will be filled with manometric fluid. It can be anything based upon the application. Okay, so when it is filled, there is nothing else. So what, this is a free surface, so here that pressure will be P atmospheric. And as we can see, like in case of fluid, and by applying the Pascal's law, in horizontal direction the pressure remains same. So here also the fluid will go up to this height only, right? Same height, because here pressure PATM, and if it goes till this point, here the pressure will become PATM and it will come into the static condition here. Okay, so when fluid is kept freely, the pressure is PATM and it will remain at the same level. Okay, so now if we connect this thing to a pipe where we want to measure the pressure P, so what will happen? This additional pressure, this fluid will come here and it will apply the pressure on this layer. Okay, and this layer will come down. Okay, this layer will come down, let's suppose by distance delta H. Okay, so this is whatever this displaced manometric fluid that will come in this pipe, right, and it will rise here the same amount. Okay, so let's suppose the same amount has risen up to delta H. Okay, my friend, what is this height now? Delta H, right? So this is a new stabilized level of the manometric fluid. Okay, my friend, this is delta H. So if I'll try to write down this relation between amount of fluid over here, that volume of fluid over here, and volume of fluid in this represented by red, then it should be same, because the fluid amount will be conserved. So whatever displaced amount here, the same amount will risen up from here, right, from this point, because earlier till here there was fluid, now it has risen till here. So let us consider the area of this pipe is small a and the area of this reservoir is capital A. So what is the relation now? The relation will be capital A, that is area of the reservoir, into delta H. This is the fluid displaced amount, and what is the, it will be equal to the fluid risen in this column, so that will be A into H. Okay, my friends, so this will be the relation. So now if I want to measure the pressure inside this pipe, okay, here the pressure is P and now it is connected to single tube manometer. Okay, now it has been displaced. So now I'll write down whatever it was written in the previous slide, same thing. Okay, so this was the earlier level, right? So here if I'll draw this dotted line, so this will be the delta H, and from here it has risen to H. Okay, and from here till here this is Y, this point, and this is delta H. Okay, so this is the free surface, so I'll be having the pressure as P-atm. Okay my friends, now I want to find this pressure P, so I'll start from here, right? So I'll write down P. I'm going down plus, what is the density of the fluid? Let us consider the density is rho F. So rho F, by how much distance I have gone down? Y. Plus, again I am going down by delta H in this fluid, right? So rho F G into delta H. Let us consider density of manometric fluid is rho M. Okay. So now I have come down to this level. Now I can move because it is the same fluid now, right? So I can move in the horizontal direction, and here the pressure will remain same as per Pascal's law. Now from here I am moving up. So I have moved up by delta H first. So minus, because I am moving up. What is the density of the fluid through which I am moving? Delta H is rho M G into delta H. Then again I am moving H. Then I'll do minus again. What is the density of the fluid through which I am moving is rho M G into H. And now I have reached to this position at the free surface. The pressure here is P-atm. Okay my friends. So what is the P value now? P-atm plus rho mercury, rho manometric fluid G into delta H plus rho mgh minus rho fgy minus rho fg delta H. Okay my friends. So now we have the expression for pressure inside the pipe. So let us try to understand why we have moved, because this is nothing but similar to U2 manometer. But why is the necessity of this single column manometer? Okay, so let us try to understand. As we have seen here, like A into delta H by conservation of the fluid volume or mass, A into delta H is equals to A into H, right? So because A is much larger than, capital A is much larger than the small a, so I can say delta H is much smaller than capital H, sorry, small h. Delta H is much smaller than small h, right? So a very small displacement here, right? So I can say delta is very small value. So this leads to high value for H. Okay, this means I am having high sensitivity, right? So a very small change in pressure, or I can say very small amount of pressure, can be measured using this device because it is very high sensitive. A very small change in delta H here leads to very high change in H, and thus it will be measurable, right? Easily measurable. So we can say it is very highly sensitive. So we use this device in case of where very high amount of precision is required. So when you use single column manometer is when you are having very high amount of precision. Okay, but for solving the question you have only one basic concept of column, that is sign convention. When you move down, you add this term to the pressure, and when you move up, you add this expression to the pressure, right? You add, and here you will subtract. When you move up, you will subtract. When you move down, you will add. Okay, I hope this is clear, right? This is for revision of sign convention. This is the sign convention. This is the only concept that you have to memorize while doing the problems. Okay, so now let us move to the one more concept, that is sensitivity of manometer. So till now what we have studied is that the column here is straight and vertical. Now if I tilt this column, so I have tilted it, right? Instead of vertical position, what I have done, I have tilted this thing, right? So now let's suppose it is at this height. This is the height, right? Okay. And now this manometer, this tilted angle, is connected to some unit where you want to measure the pressure, right? Let's suppose. Okay. So now we'll compare both the cases. Okay, so in the starting phase, what it will be? It will be at the same level, right? Here at the same level is starting phase. When there is no pressure or there is nothing, so this will be at the starting, like this. All the fluid, this will not go up, right? But when you have added this tube with pressure P, now the mercury or the manometric fluid will come down. What will happen? It will come down. It will settle down here, right? Let's suppose. And in this pipe also it will rise up. In this pipe also it will rise up. Okay, my friends? Because this has moved down. So let us try to understand now the concept. So now let us apply the concept of pressure. So now I want to find the pressure here using these two devices. Okay, only this is simple manometer, right? Simple U2 manometer. So what I have done, I have inclined this thing. Let us try to understand what happens. So in this case, let's suppose this height is H1 and this height is H2 and this height is Y. Okay, so let us try to find. So P, I am moving down, plus this is Y, rho of fluid G into Y. So now I can move into the horizontal direction like this. Okay, now I am talking about this. Let us consider this one as the first case, this is second case. So I am talking about the first case. So now I will subtract minus, right? Minus, how much I need to subtract now? Yes, this height is H3. Okay, so what I have to do? Minus rho manometric fluid H3G minus rho manometric fluid H1G. Now I have reached to top position, that is P18. Okay. Okay, my friends. So now, what is the amount that it has risen? Like now H1 plus H3, right? So pressure is same, P plus rho FGY minus PATM upon rho mg, right, equals to H3 plus H1. So this is the total height in the column 1. Okay, now let us take the example number 2. Same formula will apply. Is P moving down to plus rho FG into Y. So now I have reached to this position. Now I am moving up. But what I have to take? I have to take the vertical direction, right? Vertical direction. Okay. So this is H3, right? Nothing but H3. So effectively, if I am moving from here to here, it means effectively I am moving H3, right? Because the acceleration due to gravity is vertical. So I have to take the vertical height. So minus rho mg H3. Okay. And now from here to here, again I have to move the vertical height. So let's suppose this angle is, let's suppose this inclined by a theta angle. So what will be this height? H2 sine theta, right? So what is the effective height that I have moved up is minus rho mg h2 sine theta. Okay, and now I have moved up to the top level. Here the pressure is P atm. Okay, so now again I want to find this height h2 and h3, right? So if I'll do P plus rho f gy minus P atm divided by rho mg, right, equals to h3 plus h2 sine theta. So from expression 1 and 2 I can equate this. I can say h3 plus h1 equals to h3 plus h2 sine theta. So now h3 can be cancelled and I can say that expression for h2 is nothing but h1 upon sine theta, right? So I can say from this expression h2 is greater than h1. So it means if we have an inclined column in case of manometer tube, it can even measure much more smaller pressure as compared to vertical tube. And this factor, and it can measure by how much factor? 1 by sine theta, right? I can say h2 has come up as h1 upon sine theta. So it can measure pressure of a smaller amount up to how much level? 1 upon sine theta times it can times the value it can measure in case of vertical manometer. So what is sensitivity factor here is 1 upon sine theta. So this is called as a sensitivity factor for manometer. So this is how you will derive, and I hope now the derivation of this sensitivity factor 1 upon sine theta sensitivity factor is clear to you all. If you have any doubt, you can ask in the comment section of this video. So now let us move to our next topic, that is assumptions in manometer. So what are the various assumptions while solving the questions or while performing various analysis that we have done till now? What are the various assumptions that we made? That is, fluid is in static condition, that is hydrostatic condition. The manometric fluid or the fluid of which we are measuring the pressure is incompressible fluid. We are having negligible capillarity and sensitivity of manometer. Let us move to our next concept, that is differential U-tube manometer. So as the name suggests, that is difference. So it tells the difference between two pressure. So let us consider a pipe having a pressure P1 and I am having another pipeline in which the pressure of the fluid is P2. So what I do, I will connect these two pipes with a U-tube. Okay. And now I have filled this with water or any other manometric fluid. Okay. So this is the manometric fluid. Okay. And these are the fluid. So let us consider the density of the fluid. Here is ρ1, here it is ρ2, and now the manometric fluid density is ρm. So there are certain data that is given. So height from here till here is given as h1. Okay, and the rise in this thing is, let's suppose it is delta h, and from here to here it is h2. Okay, so now let us try to use the concept that we have learned. So we'll start from here. So here it is P1. I am moving down by distance H1 in the fluid of density ρ1, right? So ρ1 G H1. This will give the pressure at this point. So now I can move parallel. As per Pascal's law, here the pressure will remain same. Then again I am moving up. So I have moved up by delta H in fluid of density ρm, right? So minus, because I am moving up, density of fluid is ρm, G into how much height I have moved up, delta H in ρm fluid. Then again I am moving by distance S2 in fluid with density ρ2, and I am moving up, so minus, density is ρ2, G, how much height I have moved is S2, right? Now I have reached to this point, that is P2. Okay, so if I calculate the pressure difference P1 minus P2, that is delta P equals to rho mg delta H plus rho 2g S2 plus rho 1g minus rho 1g H1. So this is the expression of the differential pressure delta P. Okay, my friends. So this is the device which tells you the difference in pressure. It does not tell the absolute pressure of any fluid. Okay. So a very good application that is very frequently used in ventimeter. So let's suppose I have a throat here. Then again there is divergence. So what I know the pressure here, I want to find the pressure here. What is the P2? So what I will do, I'll connect a manometer here, YouTube manometer. Okay, and this will be filled with manometric fluid, and there will be deflection of delta H height here. So if I calculate this delta H and these H values, height from here till this point, okay, then I'll be able to calculate the pressure here, right? So this is H1, here it is H2, it's same expression will come, right? Density will be rho here also, and in this here also density will be rho. Let us try to write down. So P1 plus rho G H1, I have moved here. Now I am moving parallel to this point, and I am now moving up. So minus rho m G delta H minus rho G H2. Now I have reached to P2 point, that is P2. So I can calculate the difference in pressure P1 minus P2 equals to rho m G delta H plus rho G H2 minus rho G H1, right? So now I can derive the relations between the pressures in case of interferometer. So now let us move to our next concept, that is inverted U2 manometer. So in this case, instead of putting this manometer on the downward, I'll put in upward direction. For example, let us consider the same case. There is specific application for inverted U2 manometer. So now what I did, I have placed manometer in this fashion, inverted type. So when I put, in this case, when density of the manometric fluid is less than the density of the fluid, rho. But when the manometric fluid density is more, then what I'll do, I'll place straight or simple differential U2 manometer. Okay, this is differential U2 manometer, this is inverted. As name suggests, I have inverted it, right? I've moved up, just opposite, 180 degree. So let us try to solve one problem based upon the concept of manometer. Okay, so let us try to read the question. The balancing column shown in the diagram. So this is the diagram. Here I have a balancing column. 3 liquids. It contains 3 liquids. Here rho 1, here is rho 3, here it is rho 2. The liquid level of one limb is H1, it is given below the top level, and there is a difference of H related to that in the other limb. So now I have to find what will be the expression of H. So I don't have to think whether it is problem of U-tube manometer, inverted manometer, or simple manometer. I have to just apply that concept. So I know the pressure here, that is P. So I have written P. Now I am moving down till rho 1 is there. So I am moving down till here rho 1 is there. Now I'll calculate the height by which I have moved. It is already given, that is H1. So as I am moving down, so plus, in which fluid I have moved down? Rho 1. By how much distance? H1. Now here I have reached that this pressure will be at this point. So now I can move parallel, because here the fluid is same. It's rho 2 only. So I can move in the horizontal direction, and I have reached here, and by Pascal's law here the pressure will be same as this. Now from here I have to move up. So I am moving up by distance h in density of rho 2. So moving up, so minus in density is rho 2. By how much distance I have moved in rho 2 density? By h. Okay. Now from this point again I have different fluid of density rho 3. So then again I am moving up, so minus density is rho 3 g. By how much distance now I am moving up? Here to this point. How much will be? H1 minus H. Now I have reached to this point. Here the pressure is P. So P will get cancelled out. Okay. Now I am having expression rho 1 g H1 minus rho 2 g H minus rho 3 g H1 plus rho 3 g H equals to 0. I'll move H on one side and H1 on the other side. So H, G will get cancelled out. So what will remain? Rho 3 minus rho 2 equals to rho 3 minus rho 1 H1. So what will be the H? Rho 3 minus rho 1 upon rho 3 minus rho 2, or I can say H equals to rho 1 minus rho 3 upon rho 2 minus, right? I have multiplied by minus both ways, top down. So C is the correct option. So this is all from our today's lecture. I hope the concept related to the manometric and various pressure measurement devices is clear to you all. In case of any doubt, you can ask in the comment section of this video. For more videos and regular updates, subscribe to this channel. Thank you all for watching this video.